Good morning. First of all, I would like to thank the organizing committee for the opportunity to give this talk to everybody. Pity I'm not present here now, but believe me, I'm here in spirit. And before starting, I would like to forget chemistry for a while and pay a tribute to someone very, very important. And he's celebrating 80 years, everybody knows, and everybody knows him, Professor Dr. Gary Christian. It's funny that we met together in a very unusual situation. It was during the international meeting in Projection, Las Vegas, and I should be there together with the Professor Bergamin, but we fly in separated planes, and his flight was cancelled. So I arrived in Las Vegas without money and without your hotel reservation. And the Professor Christian hosted me, and we played casinos, and I realized that he was really, really a friend. And in 1997, he visited us in Piracicaba, in Brazil, during the International Flow Conference in 1997, and gave a very nice picture, a very nice talk. And he proved to be also a very good colleague and interacted wonderfully with everybody. And then he came back to Piracicaba a few years later as a friend and got the opportunity to visit Piracicaba, visit my family, and I was very proud about that. And since then, we always met together, editorial tasks, visiting, and so forth, and so forth. So I'd like to wish him for the next years very, very peace, health, happiness, prosperity, useful work, and friendship together with the family, especially Sue, his wife, colleagues, and friends. And also, we wish a permanent interaction with us. By the way, what about another visit to Brazil? Gary, thank you. Going back to chemistry, let's talk about the main focus of our talk. And the talk deals with fluidization. And the fluidization is a very common process and extensively used in the industry. And it consists in modifying the condition of a granular material. The granular material, usually static sodic state, it's converted to a dynamic fluid-like state. And how is doing this? This produces a chaotic yet reproducible steady geometry. And what is that? This belongs to very, very, very old story. Fluidization was mentioned in the 60s. A very famous German, George Bauer from Saxon, he described a hand-jigging operation for oil dressing. And the funny thing is that George Bauer in German corresponds to Georgius Agricola in Latin. And a famous book called De Re Metallica, in English, On the Nature of Metals, mention the fluidization. And jigging is a sorting of particles by density by rapidly alternating surges of liquid through a screen supporting particles. And upward surges a series of short-lived fluidizations, each followed by a hindering settling. This is something analogous as people make with the sand in rivers, where the water, a fluid, acts as a fluidization for the sandy solid particles. And a fluidized bed is a cylindrical column with particles through which a gaseous and or liquid fluid flows. Fluidized bed reactors, as particles inside it play a reactional, catalytic or adsorbent role. And the main advantage, there is a very large surface area for fluid and particle interaction. Potentialities, industrial separations, mass heat transfer, chemical reactions, and so forth. And the fluidized beds are applied often to industrial synthesis, water treatment, combustion, catalytic reactions, separation, mass and heat transfer, pharmaceutical production, and so forth, and so forth. That means it's a very, very known process in the industry. And there are two kinds of fluidization. One is steady continuous. Both mobile phases are in movement. Solid one, gas one, inside a large chamber. This chamber typically 1, 2, 3 meters, very, very large. And there's a figure of a distributor where gas and solid are mixed together, liquid and solid are mixed together, or even gas, liquid, and solid mixing together. And every particle starts to behave as fluid. And this generates a steady situation. It's possible to have a direct or reversal flows. And the funny thing is, the solid phase and the liquid phase tends to travel at different speeds, at different velocities. This is a fluidization, a continuous process. And we have a fluidization in a batch-wise process. The solid particles are maintained, are kept in a defined zone in space. It behaves as a static, although it's dynamical. And the liquid phase flows upwards through the solid particles, causing fluidization. But it's restricted to a special space. It's in a fixed position. Because of that, it's called a batch. And then liquid phase, fluid phase goes out. And we can have a fluidization by exploiting circulating strings also. It's the same as that in batch fluidization, but the fluid phase circulates and it passes several times through the solid particles. It's much more efficient. And this drawing gives us an impression how the thing operates. Liquid phase through here, pump, X apparatus to measure, manometers, pressure, flow meters, and then the distributor mixes with the fluidized bed and circulates. After the entire process, some valve is modified and the thing is discarded. The interaction time, so the liquid improves drastically. The main relevant aspects of fluidization. Of course, excellent fluid-particle interaction. The surface area is tremendously improved. No channeling effects. It's a chaotic geometry. There's no preferential pathways like for instance in chromatography. There is no particle contraction expansion. Particle swelling is not significant. There is not a high pressure, although small pressure particles, no very low pressure drop. The columns are very large. The entire process is worldwide accepted. And the funny thing, it is adherent to flow analysis. So, after this preamble, we can think in adding fluidization in flow analysis. This is our focus. And this was done for the first time a few years ago. And the challenges, we should promote a drastic reduction in fluidized bed reactor size. Instead, meters in height, instead decimeters in diameter, we should go to centimeters in height and millimeters or less in diameter. This follows the general tendency towards miniaturization, but it's really a challenge. Also, we should understand very carefully the flow velocity and the flow pattern. So, regarding flow velocity, fluid is introduced into a vertical bed of solid particles and the upwards displacement via empty space among particles. At low fluid velocities, low aerodynamic drag on each particle, and the bed is slightly modified. Increasing velocity, drag forces becomes more expressive and counteracts the gravitational force. In particles moving away from each other, expanding the bed volume. Further increase, a critical value is attained. The upward drag forces matches precisely the downward gravitational force, thus suspending the solid particles. Next phrase comes from the literature. The bed is said to be fluidized and exhibits fluidic behavior. Beyond this value, the bulk density of the bed is lessening, fluidization becomes violent, and the particles no longer form a bed, being wasted. So, we can perceive that there is a special velocity, a critical value, that should always be set. But this is problem number one. In flow analysis, a critical velocity is not easily attained. Why not? Because in a laminar flow, the flow inside the tube is very fast, and the flow near the tube walls tends to zero. There's a parabolic velocity distribution. So, a critical velocity is not attained with the pulsating flow delivered by peristaltic pumps. Of course, we can provide some better fluidization by exploiting pulsed flows delivered by solenoid pumps. By adding a air stream to mix. By promoting mechanical steering or magnetic fields. In this way, magnetic particles. And with pulsed flows, it's the essence of the multi-pumping flow systems. It has two states. Go is a very sudden period, a stroke at a very high flow rate is added to the system, very go. And the stop, a very long period, and the particle settlement. During go, we had the fluidization. During the stop, settlement again. Okay? The pioneering application with pulsed flows deals with the spectrophotometric determination of zinc in plant digests. So, the sample was pumped through the fluidized bed, And the fluidized bed was an anion exchanger, Daux 1-8 resin, where zinc was concentrated. So during the sampling process, the sample flew through the fluidized beds and the zinc was in line concentration. After that, the eluent eluted the zinc towards the system. Zinc-on and the buffer reagents were added, and a color was measured proportional to the analyte content in the sample. This was very funny. It was possible to concentrate it and elute it in line without any troubles found in normal chromatography. No channeling effects, no swelling effects, no pressure drops. But I would like to leave here something for reflection. Drawbacks. Let's think on drawbacks. The next application, 2008, dealt with a turbidimetric determination of chloride and sulfate in surface waters for arid regions in Brazil. This was an endeavor of our institute. In the northeast region, Brazil, it's very arid, and the water near border, near the sea, can have extremely low chloride or very high chloride. If the water presents low chloride content, it's a good water for drinking, for irrigation, for use. But if it has too high chloride, it's necessary to estimate the sulfate determination. Why? Because when the chloride comes from the aridity, the arid regions, all chemical species are concentrated. So if you have very high chloride, you should have very high sulfate. But if the high chloride undergoes marine influence, sulfate is low. So it's necessary to provide a chloride assay, inline prior assay for chloride, to decide the need for sulfate determination. Then it's necessary to perform an inline sample cleanup. And this was accomplished by a mini column with fluidized beads. Here, mini column outlet goes to a resampling party for sulfate determination. So this reduced drastically the number of assayed samples for sulfate. And with 6 assays per sample, the large bed volume was no longer a drawback. And this demonstrated that fluidization could be very useful for inline separation concentration, inline cleanup, inflow analysis. And people from Spain, a few years later, 2010, promoted dynamic extraction from heterogeneous solid samples. So it was necessary to estimate the trace metal bioaccessibility for cadmium, chromium, copper, lead, and zinc. And the samples were very dirty, solid waste incineration ashes. Very large column, 2 grams sample, 90 measurements. And this was something very, very, very impressive, because if bioaccessibility was concerned, it was important that it was very, very important the representativity of the solid samples. So they really need a large chamber, a large sample, a large fluidized bed. And they demonstrated that fluidized bed is very important for bioaccessibility assays. And now, 2017, we evaluated soil capacity for phosphate adsorption. Again, soil is a very unhomogeneous sample. It's necessary a large sample amount. So we use this 50 milligrams of soil and estimated its capacity for phosphate adsorption. In tropical soils, phosphate adsorption is closely related to available phosphate, and the soil capacity for adsorption of phosphate adsorption is then very relevant. And the machine operates like that, the flow system. The sample through the fluidized soil column, phosphate was retained. The unretained phosphate, remaining phosphate, goes to receive reagents for his determination, and the flow through detector directly provided the soil capacity for phosphate adsorption. And people from Russia, they recently proposed the concept of suspension column, ultrafine solid particles suspended inside a mini column. It's also fluidization, but it's an ultrasound-assisted process. And it was possible to determine aluminum, chromium, iron, urine, and lanthanides in seawater. And also it was possible to promote heterogeneous immunoassays. It was the same strategy, but the only difference is a very small particle. Now we are going to typical flow analysis, and the ultrafine solid particles fluidized. And it was possible to fractionate liquid dispersive systems, and this was done again by our Russian friends in 2015. And they promoted the selective retention of microparticles inside the suspension column. Again, ultrasonic assisted. And they separated Rayleigh earth elements and yttrium from natural wines, and they detected them by ICP-MS. And another possibility is to promote air-assisted fluidization. And this was done here by Andrei Bulatov's groups. And they exploited particle immobilized reagents in a SWIA system and determined the glycerol in biodiesel. And they used the organic phase sample, aqueous phase carrier stream reagents, solid beads, resin, and air for improving fluidization. And the very nice results for glycerol sorbed on glass fiber, eluted towards the column, reacted with copper, and detected as the colored copper glycerate complex. And also, they proposed a novel approach for chemiluminescent. And they combined the multi-pumping flow systems to promote fluidization, fluidized bed reactor to promote the chemistry, and the direct injection chemiluminescence. And this was done this year. It's a very new, and I'm sure most of authors are here. And they determined the uric acid in saliva. So, we starting fluidized. The concept in flow analysis is new, although industrial is very old. But it's time to think about the further research. Of course, we should investigate in details influence of flow rate, particle size, chamber geometry, etc., etc. Another point, the Schlieren effect. This occurs when solutions very bad mixed are submitted to measurement. Probably with fluidized beds, no Schlieren effect, or at least it will be minimized. Solid phase travels at different speed depending on the particle sizes. So this is fantastic for flow cytometry. We tried to find something in the literature. It seems to be nothing. For heating promoting, the mixture, heating solid liquid phase is immediate. It's forgive me the expression, is a filet mignon. And the novel applications, mainly in situ assays, immunoantigeno, ELISA, biochemistry, and the more important, microfluidics. The first phases of microfluidics was done in French, and it's a very promising, and I'm sure that microfluidization will be also possible in the field of microfluidics. So I would like to find you in person again and talk about this, because this is a defined tendency in flow analysis. And we are wishing to acknowledge Jeane Maria Cunha Machado Andrino. She did the hard work. She did PhD thesis in this theme. Valdemir Aparecido Barros for critical comments. Our Brazilian funding agencies for final support. And all you for your kind attention, although I'm not here. And I would like to invite you to visit SENA, our institute, our laboratories, to know people, more friends. Hospitality is for us the #1 priority. And last but not least, Piracicaba is a very hospitality and a very beautiful city. Thank you.